Hi, this is the Temperature Podcast, where we explore the latest open source Linux and IoT technologies and associated workflows that enable innovative teams to build products better. Today we have Chris Cole with us, so we're looking forward to discussing what he does and some of the things we can learn. So, welcome, Chris. How are you doing today?
Thanks, Cliff. Doing well.
And also Kem Raj is with us as usual. Hi, Kem.
Hi, Chris. Looking forward to talk to you today.
Thank you.
Yeah, Chris, so maybe if you can just start out by telling us who you are and what you do and kind of how you got to where you're at now.
Sure. Yeah, thanks, guys. It's really appreciate being on the podcast, and it's a pleasure to speak with both of you. My name is Chris Cole. I'm an embedded systems engineer, and I own an embedded systems consultancy that specializes in firmware development, microelectronic design, and wireless connectivity. I've been running the consultancy since about 2018, and I graduated from the University of Akron with a BSEE, and then later went back to get my MBA. And I'm currently working with 3 other electrical engineers in my company and 1 computer engineer. Prior to consulting, I was VP of Technology at Laird, which is a wireless technology company headquartered in London. And while I was at Laird, I ran the engineering department for about 7 years and had 6 direct reports and 80 engineers in total around the globe. We had engineering offices in Akron, Boston, Milwaukee, London, Taiwan, and Malaysia primarily. We had a few remotes as well spread throughout the US. And we're a publicly traded company on the London Stock Exchange, which is of particular interest to me. As you know, I was on the leadership team, and I got to spend a lot of time with other executives and learn the inner workings of this company. And I also enjoyed visiting customers around the world and learning about their business challenges, just as much as I loved leading the technology development that was being carried out across the engineering teams. Our main product lines were wireless connectivity modules for embedded systems, and primarily embedded Linux. Prior to joining Laird, I did embedded systems consulting for about 4 years, starting in 2008. And when I did that, I was working with similar technology and applications as we do today at Co-Design Development.
Mm-hmm.
Yeah, that's interesting. So Laird is called something different now, isn't it? It seems like I'd seen their name recently.
Yeah, they went back to a name of an early acquisition. I'm trying to remember what it was. Azurio.
Yeah.
So Azurio was a wireless connectivity company, like a couple decades ago, and they had a phenomenal Bluetooth team, and they did other forms of wireless connectivity as well. But they were acquired by Laird about the same time Laird acquired Summit Data Communications, which was a Wi-Fi embedded systems company out of Akron, which was started by a bunch of ex-Cisco folks. So, so they returned to their old name after a couple of decades and renamed themselves from Laird Connectivity back to Azurio, and that's what they're known as today.
Okay, neat. I wondered where that name came from, but that makes sense if it was one of their acquisitions. So at ColdED.com, or your consultancy company, what all do you do, and what kind of work, what kind of projects do you like to do or look for?
So we're a consulting company that designs and develops embedded systems for medical and industrial applications. And we design embedded systems that typically include microelectronic design. We do prototype assembly, firmware development, test, and deployment. And we tend to leverage open tools whenever possible. For example, we use KiCad for almost all of our electronic designs.
Mm-hmm.
And for firmware development, we leverage the GCC compiler suite. And for testing, we typically write all of our test scripts in Python. And we always use Git for all of our source code management and configuration management. We also use embedded, or I should say Linux on our servers and as well as on our development machines. And we end up using embedded Linux on a lot of our embedded projects. So we get a lot of use out of the, out of the outputs of the open source community in terms of tools, operating systems, and even source code that we integrate into some of our solutions.
Yeah, that's great. Excellent.
And some of the applications that we work on, they tend to be mission critical for the medical and industrial markets. So some examples on the medical side that we've done hardware and firmware development for are an implantable neurostimulator, and this will have a machine learning aspect to its operations soon. So that's an active project that we're working on. And we've developed a medical tube locator that utilizes machine learning. And we also have experience with Wi-Fi telemetry and Bluetooth telemetry for infusion pumps and patient monitors. We're currently working on a sensor-assisted total knee arthroplasty tool for surgeons to use intraoperatively. And we've also done an intervertebral replacement disc implant. On the industrial side, we are working on a vibration monitor for engines and compressors. And this utilizes AI for predictive analytics. We've also done a vision system for object detection for the automotive industry. This is a safety application, and this utilizes AI, computer vision. And we've also done a couple of collaborative robotics projects for the automotive industry.
Wow, that's pretty impressive things actually that we see here. So I think, you did some consulting to begin with, and then, you worked in between in leadership teams and learned some of the management and running a company, how things work. And then you went back to do consulting. So, and I'm sure that, all this portfolio, the impressive work you did as part of ColdED, essentially, I can see the differences between these two. But if I were to ask you, what are some of the trade-offs between working for someone else or running your own company?
Yeah, there's several trade-offs, between the two. As far as working at another company, I think, I've worked at a lot of different engineering firms, particularly in the earlier part of my career. And at each place, I would always enjoy the fact that I could learn very quickly from the other engineers that worked around me. And as I worked through various engineering challenges, there were typically, issues where a fellow engineer can help me get through it to complete a given project. So working in the teams at these companies, I was never alone, and there always seemed to be somebody around me, that can help me with a technical issue. And as I was learning the ropes in product development, working at a company that was already well adept for doing so was a great way to learn the industry and technology very quickly. So that's definitely a benefit of working at an established company. Is really just the rate at which you can learn your industry, the needs of your target customer, and the applicable technologies. For me, another benefit working at a company is the ability to work in a cross-functional team to achieve a common goal. Many projects that I work on would involve, marketing, product management, engineering, quality assurance, sales, even finance. And working closely with these other roles enabled me to develop the cross-functional skills that would later enable me to move into leadership roles within the organization. And it was a good way to really learn the business I was working in and understand it from a multitude of perspectives. When I later went to get my MBA in 2015 from the University of Akron, I found the program very comfortable to navigate, as I already had a good understanding of the inner workings of a business organization from various angles. Running my own company was a logical next step for me. Having gained the knowledge about key business issues, and gained the skills to apply that knowledge, and the confidence to take action informed by the past experience I had, I'd attained the business acumen required to start something up on my own. The big difference is that, you as a business owner are the business, and that you are solely responsible for the well-being of your employees. One of the rewarding parts of owning your own business is the independence. You're your own boss. You have the freedom to make your own business decisions that are crucial to your success. And this includes creative freedom and the ability to see your ideas come alive in implementations that you build to solve the needs of the customer. It's definitely rewarding to see the company thrive and grow. Growing our team, our customer base, our product development portfolio, and our brand has been a very rewarding experience for me.
Yeah, I think I can equate this to growing a small plant in a garden, and you always go and look out for water, and so it's a very different experience. And I 100% agree with what all you experienced through it. So this is amazing. So I think a lot of projects you were talking about earlier on. I guess you are a heavy user of MCUs, and so are there any interesting stuff happening in the MCU space, technology-wise or other, business-wise?
Yeah, I'd say I think that leveraging AI in the embedded space, in particular in microcontrollers, as you mentioned, is a fascinating area to me that's largely underutilized. This is definitely of great interest to us as embedded systems engineers who are always looking for better ways to solve complex problems. The capabilities of AI have been getting a lot of attention in the news lately, and I think that it's really exciting to be able to leverage AI on these small, low power, low cost embedded platforms. When people think about it, when they think about AI, they tend to think that a large amount of compute is required to use it, and that obviates its application in low cost, low power embedded systems. However, that's not really the case. Depending on the complexity of your AI model, it may fit and run acceptably well on a small edge device. In training is typically the computationally expensive part, and for mostly embedded applications, the training can be done offline using computers with more computational horsepower. And then once the model's been trained, it could be deployed onto an embedded system, and there the model can be inferenced very quickly by an MCU, and this is on the order of tens of microseconds per inference, depending on, of course, on your MCU speed and the size of the model that you're trying to inference. But the inferencing is very, very quick, especially in contrast to the speed of training. And in some cases where a machine learning model is designed to undergo continued self-training in the field, which is what machine learning is all about, this may still be possible since the training cycles that will be executed in the field will occur at a very low rate, much lower rate than the original training of the model when it took place. So these are what we call overtraining cycles. And these are the backpropagation cycles that are performed periodically on top of a pre-trained model. A single training cycle doesn't take much time. It's we're talking milliseconds, as opposed to a full model training, which can take tens of minutes or several hours on a high-power desktop. I think going back to interesting technologies on microcontrollers, there is the introduction of NPUs in MCUs. So an NPU is a neural processing unit, and we're starting to see these getting stitched into microcontrollers. And general microcontroller cores, such as the ARM Cortex-M33, that's really popular today, can deal with lightweight machine learning computation. But an NPU provides a significant performance boost while utilizing less power. So this will enable more complex machine learning models to be handled on chip, as opposed to that work being offloaded to the cloud. So this gives rise to edge AI applications becoming more real. And there are several silicon vendors that are working on NPU-enabled MCUs, including NXP and ST Microelectronics, to name a couple.
So to linger a bit on this one, say NPUs, is there some like a standard design for this, or there are like custom NPU designs? What do you see in the marketplace?
Yeah, currently, so I haven't worked with an NPU yet, but I'm reading about them, and I'm anxiously awaiting the arrival of an NPU and an MCU from any of the silicon vendors. And I have been watching ST Microelectronics pretty closely. And they have a couple of models. They have one they've been working on for a couple years now called the STM32N6 line. And that will be some kind of an ARM Cortex-M with a neural processing unit stitched in with it. They're working on an evaluation board for that, but it's not yet available. Very recently, they have made available an MPU board with an NPU. So ST Microelectronics not only makes microcontrollers, but they also make microprocessors. And for several years now, they've had a line called the STM32MP1. And you can run embedded Linux on it, and it employs an applications processor, a Cortex-A class. And this new processor that they just released is the STM32MP255A. And in the MP255A, I believe it's a dual-core Cortex-A. I forget the model, the specific model, but then it also has an NPU with it as well. So that's for much higher performance AI applications at the edge. So it's still, a small, low cost, low power microprocessor, but it's not quite a microcontroller. So they kind of have a NPU offering in both types of chips.
Yeah, and you have NXP with their IMX93. We have a few here, but I've not done anything with it. But I assume that would be similar with the neural processing unit built in.
Mm-hmm. Yeah, and as far as the what it looks like from an applications developer and how consistent that's going to be from vendor to vendor remains to be seen. Mm-hmm. Because it is so new. So what ST does is they have they have their Xcube AI plugin, which is implements various AI algorithms in a closed source black box fashion that you can link into your application. And then you use a online application to import or create your models, and it will create a binary blob for you to link into your application. And that's what they're offering for microprocessors and microcontrollers that they sell without NPUs. And then also with the advent of the new micros that they're coming out with that do have an NPU, you can use that same online tool that'll create a linkable binary blob that you can then download and include in your application. So their tool will be obviously proprietary in terms of what the user sees and how the user interacts with it, as opposed to more of a lower level, C-style API that you might be used to when you're working with traditional AI tools like TensorFlow or TensorFlow Lite.
Mm-hmm. Mm-hmm. So have you used any of the open source microcontroller AI solutions yet, or have you focused mostly on like the ST toolkits for your applications?
Yeah, I have. So I have used TensorFlow Lite in a couple of applications, and then I've also written my own neural net library that I've open sourced and put on GitHub, and that's been up there for about 4 or 5 years now. And I've used that in a couple of applications. That technology is, it's pretty much, how do we say, it's like a commodity technology, right? The technology, the code that will actually do the training backpropagation of a neural net as well as the inferencing through the neural net. The code itself is pretty simple and pretty straightforward, and there's a lot of really neat tutorials on how that process works. And when I was first getting into AI, way back in 2018, 2019, I decided that writing my own neural net library would be a great way to learn the inner details on how the mathematics works. And it's been really rewarding. It gives me a good perspective on how AI works at the lowest code level. But there are other ones available as well. Microsoft has a popular one called the Embedded Learning Library, ELL. I haven't used that one myself. And there's a few others, but I think I'm most comfortable, obviously, with the one that I've written. But as far as the open source ones, TensorFlow Lite is really hard to beat.
Sure. And maybe just to kind of back up to the application, can you give us an example of like a problem that was really a good fit for AI that would be pretty hard to do with just straight line code, like we used to do?
Yeah, absolutely. So a few years back, I was invited to work on a system that this is for a medical device vendor in the area, and they needed a system that would locate the tip of a tube within the body of a patient. Mm-hmm. And it was required that the tip needed to be tracked to within a couple of millimeters within the volume of any given patient. And when I was introduced to the project, they were using an array of magnetometers to track a magnet that was situated at the tip of the tube. And the basic idea was to track the magnet using magnetometers. It sounded easy enough, but they were having trouble with the math and getting the accuracy they needed. That's why they reached out to me originally. And it definitely ended up being a lot more complex than any one of us had hoped. Mm-hmm. Taking a purely algebraic or trigonometric approach to approximating the location of the magnet from the magnetometer readings proved a lot more difficult, primarily due to the bipolar nature of the magnet and the effect it had on the magnetometer readings. And the deepest that we could ascertain the location of the tip of the tube within the body was about 3 centimeters. If it was much deeper than that, we couldn't tell where it was at. So they got the idea to apply a neural net to solve the problem. And in general, anytime there's a signal hidden within a lot of data, but it's not obviously detectable, a neural network can typically pull the data out from within the noise. So neural nets are very good at detecting patterns. By leveraging the neural net for that application, we were able to increase the depth that we're able to track the tube within the body of the patient from 3 centimeters all the way down to a depth of over 15 centimeters. And we're also able to remove all the data averaging that we put in there from the prior algorithms because there was so much noise and so much uncertainty. We completely stripped out all of that averaging because it just wasn't necessary after we employed the use of the neural net.
Wow, that's amazing. Yeah, we're definitely in this day and age flooded with data, especially as IoT platforms and applications take off. We're getting tons and tons of data, so this is really exciting to see that there's new ways to parse through this data and extract useful information. So yeah, it's really neat. So we've talked quite a bit about the platforms so far. Is there anything else on the technology platform front you'd like to mention or talk about?
I think as far as platforms, most of so speaking about edge AI and the platforms that you may typically find in those applications, a very, very popular one that you come across in computer vision specifically is NVIDIA Jetson. And I had the privilege to work with the NVIDIA Jetson on a project about a year ago. And what it is, it's a edge AI computing platform for deep learning and computer vision application that runs embedded Linux, and it has a rich support for C and Python-based applications. And its embedded CUDA cores are really what make it stand out. And the project I used it on was an object detection system for a safety-related automotive application. And interestingly enough, the model I used was one from Salesforce, and it was called Blip. And it is a pre-trained model that you can download, and you could run using a very simple Python framework. And it had the ability to parse all the objects in the field of view of a camera that you attach to the Jetson. And it would literally tell you exactly what it saw. It would describe the scene. So we're able to build an initial prototype just by grepping for object names that we were interested in, and found this to be a really effective prototype for the solution. And as far as the ultimate product, we are in the we're currently working on reducing the size, cost, and power consumption of that solution. So the NVIDIA Jetson will consume about 5 watts of power continuously when it's doing its work, which for this application would have been acceptable, but we're still going through the exercise of reducing its cost and footprint for the ultimate application. Another application or platform is the Portenta H7, and this is an Arduino compatible device. It supports TensorFlow Lite and can be used for computer vision applications as well as other machine learning applications. It's put together very well and has different shields that you can connect to it that have different types of cameras and sensors. But I think that's definitely another edge AI platform that's mentionable. And I'd say that the majority of our platforms, initially we do use devices like these for initial evaluation, but when we go to productize things, we roll our own platforms, and everything we do is pretty much custom. I will say, with the exception of the Raspberry Pi CM4, we use that in a lot of applications, and a few of our customers are very comfortable with using that as a component of their bill of materials because it's so highly integrated and easily accessible. But I think the CM4 is definitely worth mentioning as well.
Mm-hmm. Sure.
So you talked about a nice application of neural net, and so I think that took me to think about that there is so much of applications out there. There is so much of data, and there's so much to solve. So what are some of your steps? Some of the things that you learned through your extensive experience of developing these apps. So what would be, if somebody were to do a application or a solution development, then what are a few things that they can learn from this? It will be good if you can share some of those steps, so to speak.
Yeah. So within the scope of developing a neural net solution, I guess what I could do is kind of describe these steps within the context of the tube locator application that I just talked about. Mm-hmm. So the first step would be to define what are you looking for? What's the desired output of the system? And in the tube locator project, there were 3 linear outputs that we were after, which were the X, the Y, and the Z location of the tip of the tube within the body of the patient. Second, you want to understand the appropriate inputs to the system. What do we need to arrive at the outputs that we're after? And in our setup, as I described, we had an array of magnetometers, and in particular, we had an array of we had a 4x4 array of 3-dimensional magnetometers. So this yielded 48 linear inputs for the neural net to take in. So if you can imagine the neural net, if you will, you have 48 linear inputs. That's 48 neurons on the input, and then you have 3 linear outputs on the other side coming out, so the X, a Y, and a Z. The next step is to build up your training data. And this is where you acquire the data that you're going to use to build or to train the model. And again, going back to the tube locator, I reconstructed a training set by moving the magnet across a cubic volume that represented that of the human body. And I would capture all 48 sensor values, the X, Y, and Z from each of the magnetometers. At every single position, I would hold the magnet in, and I did that about 1 centimeter apart in the X, Y, and Z cubic volume. Creating this data took a couple hours to generate, and in the end, I ended up with data that was several thousand rows or observations long. This data was then separated into training, validation, and test data. The next step after acquiring the data is you're now ready to construct the model. This is by far the most complex part, and this is where experience with doing this really pays off. Constructing the model is, and I should say constructing a good model is critical to attaining the desired accuracy. And it does take a lot of time to get it right. There's no manual, there's no book that describes how to construct the best model from scratch for a given application. This know-how can only come from experience. And when constructing the model, you already know the inputs and the outputs. We've already defined them. And this bounds our input and output model in terms of neurons. But the question still remains, how large or complex should the model be? Do we need a basic feed-forward network? Do we need a recurrent network? Do we require a convolutional neural network? How many hidden layers should we have? How many neurons per layer? What activation functions and biases should we use for each layer? For CNN, what kernel should be used? Do we need pooling or dropout? So needless to say, it takes quite a bit of trial and error and to get this right. And in the tube locator application, the model ended up being a basic feed-forward neural network with 2 hidden layers of 50 neurons per layer, no bias. And I use a rectified linear unit activation function for all the neurons in both layers. So the next step, after you take your best stab at creating the model, is you want to train the neural net with the training data. And remember, from before, we took all that data and we divided it into 3 different sections, 3 different types of data. You have training, validation, and test. You take the training data, which is typically like 80% of your data, and for larger, more complex models, you need more training data. You need to be careful that you don't under or overtrain your model. An undertrained model won't provide the accurate results and will result in underfitting of the data. This often results in nonsensical hallucinations on the output. And you've probably heard where some AI algorithms will hallucinate. And this is exactly what it comes from. That means that the model was bigger than the data was used to train it. So there are unexplored regions within the model from which you're trying to pull information out of. So that's when you don't have enough data to fit your model. On the other hand, you can overtrain your model, and although the output there will indicate that the model performs really, really well on that training data, it won't perform well on unseen data or new data. So this is what we call overfitting. Finally, you want to benchmark the model using the validation data. And so we've taken the test data to train the model. We now feed it, a smaller subset, maybe it's 5%, maybe it's 10% of the data that we collected earlier. And we want to feed it into our model and look at the performance of the model and see, are we happy with the accuracy? And what we'll find typically is we won't initially be happy because we haven't made any adjustments yet. So the adjustments are made to what we call hyperparameters. And there's hyperparameters are aspects of the model that we make from the outside. It's like how we train the model. So for example, we may choose to change the ratio of our train versus test data. We may choose to increase or decrease the learning rate. The learning rate is basically the size of the steps you take on your gradient descent when you're doing the training cycle. A choice of activation function is critical on each of the layers. And the activation functions they're what give a nonlinearity to your model that enable it to learn nonlinear aspects or behavior of real world data. So a real popular activation function is what we call the rectified unit, ReLU. And I use that one a lot, probably more than most activation functions. And this is really a function that a neuron will pull the output of a prior neuron in, and I should say prior neurons. It pulls it in and it has it through the activation function to modify that value before triggering subsequent neurons. And if that were just a linear function, the neural net would not have the ability to learn a nonlinear behavior. So that's why we choose things like a sigmoid or a rectified linear unit, something that's nonlinear. So the choice of what activation function to use in which neurons is important. Another hyperparameter is the number of hidden layers or the width of each layer. The dropout rate. Dropout is interesting because it's basically, as you're doing the training and of your model, you can have certain neurons get ignored, and their contributions to the output are ignored. And this is a technique that could be used to introduce a little bit of randomness, which may actually help the result a little bit. And this is to keep some models from overfitting. The number of training iterations is critical. That's a hyperparameter. The kernel size or kernel type you use in a CNN is another choice. The pooling size you may use in a layer has a tremendous impact on speed and accuracy of a model. So all these hyperparameters are in contrast to the model parameters themselves. So the parameters of a model are the weights within the model. The model parameters are what constitutes the model itself. So when you train a model, you take that and you go to do something with that model, you're talking about the values that describe the weights of each neuron. And those are the parameters. But the hyperparameters, that list of items that I was just talking about, those are what the AI practitioner has at their disposal in terms of knobs and levers that they could use to tune how that model is trained. Knowing how to adjust those, it really just comes from experience. Which knob do you turn? How far do you turn it? How to interpret the result? It all comes from experience.
So is that all like manual process, or is there a feedback loop that you can feed that data back and then run another session of training?
Yeah, you certainly can. I haven't done that myself, but there's no reason you couldn't set up like a loop, to loop through and automate some of that. Absolutely. And after you do the benchmarking, you want to do the final testing of the model. Right. And this is where you take that last bit of data that you saved. You didn't use it for training. You didn't use it for validation. You're saving it just to test that final model. And this is critical that it's unseen data so that you know how your model performs to data that that it's never seen before. When you run that test and you're happy with it, you're now ready to deploy the model. And this is the last step. And what it means within the scope of an embedded system is simply how you integrate the model into the device firmware. Generally speaking, the developer will need to plumb the data sources from the embedded systems, whether they're coming from instrumentation, the A to Ds from micro, whatnot. As soon as we have that data ready to process, we plumb that into the model input. And similarly, you want to connect the model outputs to the part of the firmware that returns the result. And an inferencing engine is required, and there are several to choose from. And we talked about this a few moments ago. In the embedded space, a popular choice is Google's TensorFlow Lite, and that was developed by the Google Brain team of researchers. I also mentioned that the X-Cube AI from ST Microelectronics is available if you're using STM32-based hardware. And then there's the neural net that I wrote a while back, which is on GitHub. And it's under the name Synthint AI. And Synthint stands for Synthetic Intelligence. It's an AI LLC that I created at the end of last year, under which I do my AI work and keep that kind of separate from the cold DD work that I do for general embedded systems. So Synthint is definitely something that I want to be able to grow and take to the next step. So right now I have a GitHub for Synthint, and that's where I keep the open source neural net. And when you're deploying the model onto your embedded system, you can take the model itself and put it right in the flash memory of the MCU. If it's a machine learning model that will be undergoing continued self-learning field, then you want to put the model into a volatile area or RAM-based model. And in this case, the model weights can be modified at runtime. And they could be periodically saved to flash or saved to an SD card or uploaded to the cloud if we have connectivity. And one of the problems that one might encounter at this stage is that the model is too large to fit into available memory, whether it's flash or RAM. And in that case, you need to go back and revisit the construct of the model and reduce it somehow. So this either means reducing the number of inputs, the number of outputs, or more commonly, the number of hidden layers or the layer widths. And alternatively, another real popular method to reduce model size is to adjust the data type that's used to store the weights of each neuron. So for example, you may not need 32-bit floating point weights for all the neurons. You might find that you can reduce those representations down to 8 bits or even 4 bits in size. And when you do this, they call this model quantization, where the information stored in the model will obviously become less, but it may not be completely destroyed. It may still be quite usable. It may be worth the trade-off to reduce some of the informational density in your model in exchange for a footprint.
So we lose some precision by doing that, but it may be a decision to be made at that point. Is that right?
Yeah, exactly. Yep. And even if the model fits in the available memory, you may still find that you have a different problem, and that is it may take too long to execute an inference, depending upon the demands of your application. So if you have a real-time application, you don't have time to wait for an answer to propagate through your neural net each time. If this is the case, you need to go back and revisit your model and simplify it further. So again, here you have a trade-off of execution versus accuracy. And to give you a feel for some model sizes in my experience, so the tube locating model that I did was about 200 kilobytes in size. And I also did a handwriting recognition model that would recognize the MNIST set, if you're familiar with that, as drawn on a tablet. And that was about 200 kilobytes in size as well. More recently, I implemented a large language model onto an MCU, which was quite a fun project. And its model size was 25 megabytes, which is that's pretty big in contrast to 200 kilobytes. But when you're talking about a large language model, those are typically, 50 or 100 gigabytes in size. And to be able to think that you can leverage that technology on an MCU is generally unthinkable. But you really restrict the domain of your corpus of information that you're training your LLM on. It's very realistic to take a greatly reduced corpus that is information on a very specific topic and reduce it to an LLM model that is 25 megabytes in size. Anyhow, just to give you an idea, these are all very, very embeddable, so you can realize some pretty impressive functionality of a neural net right into a microcontroller's memory.
Yeah, that's amazing. So like a 25 meg model, would you put that in an SD card then, or?
Yeah.
Yeah, okay.
The 25 meg, what I did is there's a couple platforms that I've got here. One is a ST Nucleo board, and the other is a camera module. And they both have SD cards, and they also both have an SD RAM that's 25 megabytes in size. So what I do is when the code boots up, it will load the model from the SD card into RAM, and then it executes it out of RAM. I couldn't memory map the SD card, the contents of the SD card into like an address space to make it compatible with my inferencing engine. So the next easiest thing was just to have the loader bring it into RAM. And these platforms both have a 32 megabyte SD RAM soldered onto them. So that was a workable solution.
Wow, that's great.
It's definitely, a lot of steps involved, and there's a lot of complexity. As I mentioned, it really relies upon the experience of the practitioner having done this many times before, and you get better at it. You build an intuition on how to build these models and how to tune them to get the performance that you're after. But not everybody has that. So there's, these steps I outlined to develop an embedded AI solution. There's a lot of detail. Experience plays a role, but there's some cloud-based AI application builders out there whose aim is to simplify this process. And what they do is they offer ready-made, off-the-shelf models for a variety of applications. So, model selection can be done online, and some degree of tuning these models, as well as the training of the models, is all done on their web-based interface. And however, I tried one of these services out. My experience with that type of offering is not good because I found the lack of availability to fine-tune the model construct to be very limiting in poor accuracy. But there is kind of an in-between idea, and this is one offered by ST, where they have a cloud-based edge AI offering that they do allow you to load a pre-trained model that you create yourself, and then they integrate a closed source inferencing engine around it and give you a binary blob that you could then link into your embedded application, which seems to be a very acceptable way to go. From my opinion, the developer really needs to have full control over the construct of that model.
Yeah. So do you think a Linux equivalent of LLMs coming in future, which can be adapted to various kind of workloads and scenarios? Or
yeah, there's some off the grid, so to speak, LLM models that you can download that fit into the available memory of your GPU. So you have a 4090, you have, 24 gigs or something like that. And some of these models are, half of that you can download and run on your own computer. I think if you Google for local LLM, and there's some options out there. And then there was an application that somebody showed to me a while back, and I forget the name of it, but it integrated into the shell, into the Linux shell. And I wish I could remember the name of it, but basically it gave you the power of an LLM right from the Linux shell, and it would interactively offer you feedback and advice, live. So I
Oh,
thought
is it the warp terminal or something like that? I don't know.
doesn't ring a bell. It
Mhm.
was a four-letter word. That's all I remember.
Mhm.
But yeah, to answer your question, there's definitely a demand for that.
Mhm.
I think we're going to see more and more of it.
Cool. So I think, what do you see happening in this interesting space in coming future?
So I think that more embedded systems developers will realize that AI can be leveraged for their solutions, and that the embedding computing hardware becomes more capable over time. And the addition of the technologies such as NPUs and more efficient AI algorithms is all going to come together and be a logical progression for us in our field. So I think we're going to start seeing a lot more people talking about leveraging AI on edge devices and low power, low cost microcontroller based devices. I also see a lot of innovation taking place, as you just mentioned, within the LLM space. There's a lot of demand there. We're all very wowed by the technology, and it seems to be getting a lot of attention from researchers and funding by companies who
Yes.
are all seeking the holy grail of AGI. And I think embedded systems will likely benefit from this innovation and progress.
Mhm.
Um, there's not a lot of obvious applications to an LLM on a microcontroller, but I think I look to discover some interesting applications of it in the future. It's technically possible right now, um, as I mentioned before, but I think LLM technology in general will continue to improve. Uh, the other the other thing that I expect is right now a problem with AI is explainability, and that is to say, how did you arrive at the result that your AI algorithm yielded?
Mhm.
And right now, there really is no good explanation. You can point to your model, you can point to how you trained it, but you can't really describe exactly how it arrived at its result.
Mhm.
So this causes a bit of concern for some applications that are sensitive to where they really need to fully understand all of the logic of how we got from the inputs to the outputs.
Mhm.
So they call it AIX or AI explainability. There's a lot of people working in that area of AI to try to figure out ways to explain, how the results were arrived at.
Mhm. Wow, that's pretty cool. Very interesting. So I guess that it's like, we humans, we do the same way. Like you ask us to redo the same thing again and again, we might error a little bit here and there. So I guess it's getting in that same realm where we don't have like the internal process to reproduce like the exact same thing. Like, playing sport or something, you
Mm-hmm.
might hit a home run and then you say, hey, can you hit it again? And it says, well, maybe not.
Exactly.
Yeah. Yeah, Chris, this is super interesting. So, is people graduating from college or people looking to start companies? Do you have any advice?
Yeah, I would say learn what you can about AI and ML. The field is growing very rapidly, and it's definitely very exciting to see, how fast it's growing. Understand the underlying math and statistics that make it work, and that'll help you to understand its limitations as well as its potential. Keep track of the developments in the area of AI by following key people and companies in the space. I'd also say that in general, you want to learn all the aspects of the company that you're working at. It'll pay dividends later if you decide to move into management or if you decide to start your own business uh, down the road. And lastly, I would say master the art of communication. Specifically, learn to convey the most amount of information in the fewest number of words. you want to understand your target audience when communicating and tailor your story appropriately.
Yeah, that's great advice. So in any as we try to keep up in our industry, do you have any suggestions for books or podcasts or other sources of information?
Yeah, there's a few notable people who've really been influential to me in the field of AI. The first one is Jason Brownlee, and he runs a website called Machine Learning Mastery. And he's an AI engineer with a master's and a PhD in AI, and he's written a number of ebooks for educating engineers in the field of AI. All of his books have easy to follow Python examples, and I've purchased all of his books and appreciate his effective conveyance of information on some tricky topics. About once a year, he does run a special where you can buy all of his books for a really, really good price, and that's how I was able to acquire all of his ebooks. I did that a few years ago, and it's definitely a treasure trove of information. Another individual I follow on Twitter is Andrej Karpathy, and he's an AI engineer who led the AI team at Tesla up until just a couple of years ago when he went on to work for OpenAI. And then he just recently launched a new startup called Eureka Labs, which is an AI education company. He also has a YouTube channel with some really cool tutorials on how AI technology works from the ground up. One of my favorite videos is named "Let's Build GPT from Scratch," and he does just that using Python in a 2-hour video. He also has a lot of incredible code available on his GitHub account. Another individual is Jan LeCun, and he's a chief AI scientist at Meta. And I like his views on AI. I really like what he and Meta have been doing with their Llama models, insofar as making their large language models directly available for use by the public, as opposed to only being available via a web API. There's a number of interesting companies and development groups I follow as well, including OpenAI, Google Brain, and Hugging Face.
Yeah, that's interesting. So is Hugging Face, is that a company or is that a community or what?
Yeah, it's a community where people share a lot of models.
Okay.
Even companies will upload their large models to Hugging Face to warehouse and distribute.
Okay.
Yeah, and then they have a UI, that basically you can leverage to build their own, way to consume it. It's sort of like really good, infrastructure to share, and I think it'll grow into like one of the marketplaces in future, but remains to be seen.
Yeah, absolutely.
Mm-hmm. Yeah. Well, I've learned a lot, so appreciate your time, Chris. Anything else, Kim or Chris, that you want to share?
Yeah, I think it was a good learning experience. Thanks. I want to thank Chris for this, and and all the listeners. If you have any feedback, please reach out.
Yeah, we're always looking to hear from our listeners. You can reach out to us a number of different ways. So thanks for listening, and we'll see you next time.